we've seen the definition of range minimum queries, and we've seen the sparse table solution. But really, to get below this n log n pre-processing time, we have to look quite we have to look a good bit more at the structure of the problem. And the Cartesian trees turn out to be the right thing to look at for this problem. All the time I was talking about range minimum queries, but really for the graphical way to define these trees, it's much more convenient to have maxima instead of minima. It's obviously the same thing, but just to warn you, so on the following few slides, I'll use the maximum instead of the minimum, because then we can draw elements, the numbers in the array, just as these bars. So you've seen that last time. So I'll speed up a little bit. The range minimum query in a certain range can then be found graphically by sliding a line across this range down, and then the bar it hits first is the range max. Okay, so our task is to look at the array A and then to find this first bar that's hit in ideally constant time. What now is the Cartesian tree? The Cartesian tree is built as follows. You take the entire range and you slide this scanning line down until you hit the first bar. That's the total the global maximum of all the numbers in the array. That becomes the root of a binary tree. And then the two lines independently continue to slide down. So this one goes down until it hits here, and the other one goes down until it hits here. And that gives us two more nodes, which are again the global minima, the global maxima, but only in the range to the right of the previous node or to the left of the previous node. And as we keep going, it's not just left of a node or right of a node, it's both. It's this line now is the one that hits this bar, is the range between these two previous nodes that we've already seen. So in the next step, we find this as the next minimum and this maximum, and this at the next maximum. If you keep building this tree like that, you get a tree. It's a binary tree, like binary search trees. Every node has a left and a right child. Some nodes have only one child, like node 9 here. It doesn't have a right child because there's nothing in between 9 and 10. So nodes can have only a single child or no child, like these nodes down here. But if they have a single child, it's important whether it is a left child or a right child. Binary trees, exactly like for binary search trees, the same types of structures arise here. Range minima in the array correspond one-to-one to finding lowest common ancestors of nodes in this tree. And that's where this Cartesian tree becomes interesting. That's why it helps us, because it allows us to get rid of the array altogether. And that works as follows. So this is something we haven't discussed a lot in the binary tree chapter. It probably was mentioned in the videos, but I think I didn't particularly talk about it. If I have a binary tree like this one, I can label the nodes in order. I did that here. That's essentially left to right orders, in particular the way I drew the nodes. You see that this is just counting from 1 to 20 if I go left to right. And of course, that's the indices in the array, which they start here with 1. I've prepared that figure earlier. Now, we should really start with 0, but not to mess this up, I'll keep it with a 1. Sorry for the inconsistency with the rest of the slides. I can define these numbers also just looking at the tree and taking away this array. And also the tree is drawn here in a particular way, but this is again just how it came from these bars. I can take that away and move the nodes just at the y position according to their depth in the tree. Now this is just a binary tree, and I have no obvious connection to this array that we started with anymore. And what's more, I can still assign numbers to this tree. The in-order numbers are given by starting at the root. So let's see if I can do this somehow. So we start at the root. Now we don't assign a number to the root. We first recursively go through the entire left subtree, and once we come back, we assign the next free number to the root. Now, a priori we don't know what that number will be, but once we come back, we'll figure it out. And then we recursively continue in the right subtree. So let's see how this goes. If we go down here, so we keep going down to the left without assigning numbers. And then the first number that we do assign is this one, because it's the first node where we can't continue further to the left. So we have dealt with the left subtree of this leaf, because there's nothing to do really. And then we're done with the left subtree, so we return to this node and assign the next free number. And that's the first one, that's 1. Then we would recursively deal with the right subtree, but that's empty too. So we go back one step up. And now we would assign the next free number, because for this node we've dealt with the left subtree, and now assign a node, assign the next free number to that node. And once we've done that, we would go to the right subtree of that node. So we do that. And again, first handle the left subtree, but there's nothing really to do. So the next free number gets assigned to this node. Then we would take the right subtree, but there's nothing to do, so we go back up. Now we have handled the entire subtree of this node, so we go one step up. And for that node, again, we have handled the entire left subtree, so we would assign this one the next free number and continue with its right subtree. But that's empty, so we just skip back up the tree. If you continue doing this, you will get these numbers that we've seen before. So here they still are. You can see you get 1, 2, 3, 4, 5, and so on and so forth. So we don't have to, what I'm trying to say with a lot of words is we don't have to store these numbers. We don't have to store them because they're implicitly encoded in the shape of the tree. By just knowing which nodes connected to which with a left and a right pointer, we can reconstruct those numbers. And if we have those numbers, we can also find the nodes that have, for our range-min query, we had the range 7 to 15, so we were interested in range 7 to 15. So we can also find in this tree the nodes that have this in-order index 7 and 15. And for those two nodes, we find the lowest common ancestor. That's this node in the tree. And then the result to the range-min query was 10, which is nothing but the in-order ID of that node, the in-order rank of that node. So again, once we have computed all those numbers, we can still answer range minimum queries if we have only given the tree. So Oh, come on. And that's the Cartesian tree. The Cartesian tree is exactly this binary tree. We can still find the answers to range-minimum queries by looking up the nodes of, if we have I and j. How do we do this? Maybe it's worthwhile writing this down. We could do this by find the nodes, with in order ID, I, and j. Second step, find their lowest common ancestor. For third step, return in order index of this LCA. I should stress here that this is a valid algorithm to compute range minimum queries, but it's not a fast algorithm, at least not unless we have a fast way to find these lowest common ancestors. It's conceivable to find the in-order indices and nodes, so the mapping between in-order numbers and nodes, that can be done with an array or with a dictionary fairly fast, but finding the lowest common ancestor in a binary tree is not per se easier than the range minimum query problem. So all I'm saying here is, in terms of the information we need about the array, to answer range minimum queries, everything is encoded in the Cartesian tree. We don't have to know the numbers that are in the array. That's not so surprising because it's a comparison-based problem. But it's still fairly helpful to realize that the Cartesian tree exactly encodes the answers to the range minimum query problem. Now, at this point, I want to stress that it was very important that we defined the problem like we did, that we return the index of the range maximum and not the value itself. The in-order index that we return using the Cartesian tree is the correct index. But we've totally lost the array contents, so we don't know what the numbers in the array really were. The only thing we still know is where the maximum was. Okay, so this is important here. If we were asking for the actual value, this would not work. We need the array. But if we're only asking for the index, we can answer the range min queries without having the array at hand. We can completely forget the array. We can delete the array once we've built the Cartesian tree. All right. Here's a bigger example of a Cartesian tree, and it's drawn in yet a slightly different way. And I think it's insightful to study that example in some details. So let me zoom in a bit. First of all, down here, that's the array. It's fairly small. I'm not sure if you can read it. But maybe let me try to zoom in first a little more. So here are the numbers. That's the array. And they're just given in the order they appear in the array. And now I make a node in this 2D grid above a certain number, and I go one step up in the grid. If that's a 1, I go 6 steps up, 1, 2, 3, 4, 5, 6, if the number here is a 6, and so on. Which means the nodes are just drawn using the index in the array as x coordinate and the value of the array as a y coordinate. So it's a plot of these points, 2D points, where if you want, this is I, the index in the array, and this is A of I, the value at this position. Now, we can find the Cartesian tree very easily if we draw the points like this by doing this slide a line down algorithm that we've had before. First, we take a line that spans the entire range, and we slide that down until it hits the first point. That's this guy. That becomes the root of the Cartesian tree. And it also separates the rest of the points and the array into two parts, namely everything that's left and everything that's right of that point. And now we treat these parts completely independently. We built the same procedure, builds a tree in those two parts separately. So let's do one more step. We take a line that spans this range, but not extending beyond those separator lines, and it slides down until it hits a node. So that gets the root of the right subtree, so we connect it. And again, that defines a separator which separates the array and the points into two parts, except that in this case the left part is actually empty. There's no more points in that range. The same thing we do on the other side of that node. So we take a line here and slide it down. It doesn't get very far before it hits this node. So we connect that to the root. That's the left child. And again, that also splits the array into two parts. And here the left side is just a single node and the right is a little bigger. So that's how you recursively construct the Cartesian tree, just shown on a second example. And one more time, I can take this tree and now forget about the height of the nodes. Here the height of the nodes was exactly the value in the array. The tree doesn't change if I just move the nodes up, so that always, if I'm at depth 1, there's one edge from the root to a node, I'm one step down from the root. That's what I did here. It's the same tree. I hope you can make them matching. And so here's the root that matches, then the right subtree matches here, and this here. So it's the same tree, except that it's drawn a little differently. And also the numbers in the nodes, I don't know if you can still read that. So the numbers in the nodes now are, I just replaced them with the in order rank. Whereas here we had here I had the value of the array copied into the node, so this has changed. But the tree itself doesn't know any of those numbers. The tree itself is just the shape. So the tree would just be, oh, you can't see this. The tree would just be, there's a node, and then there's a left and a right child, and the right child doesn't have a left child, so it would only go like this. You have two more children here to the right. There's one more here, ba-ba, ba-ba, ba-ba. And well, I'll skip the rest. So this is the Cartesian tree. All the numbers are just there to help you understand what's going on. So another example, I hope that makes clear how the Cartesian tree is built. And we've also discussed how you can use the Cartesian tree in principle to answer range-min queries. But it's not at all obvious how to find the lowest common ancestor of nodes. So even though all the information is encoded in the tree, it's not obvious how to get it out efficiently. And here again, well, that's just the same tree drawn without the separator lines to make it a little more visible what the tree looks like. Now, why do I obsess so much about going from arrays to Cartesian trees? The reason is that there's many different arrays that actually lead to the same Cartesian tree. For example, I can take the array 10, 100, 7. That will lead to the Cartesian tree that looks just like this. Here's the maximum and then the two elements here. Well, of course, I could have, instead of using arbitrary numbers, I could have reduced those to 1, 2, and 3. So this obviously is the same, because all comparisons are the same, to 2, 3, 1. But note that this is not all arrays that generate this type of Cartesian tree. I could also have used this ordering of the numbers 1, 2, 3. This is also the same, because it also gets this same tree. The maximum is here, and then the maxima in the left and the right subtree are these ones. In fact, in the Cartesian tree, it's impossible to distinguish which of those two outside elements is smaller or bigger. They're incomparable from the point of view of the range minimum query problem. And that's an important point, because it means we have much fewer answers to the range minimum query problem than we have permutations. So this is where we enter the more advanced material. And if you have questions at any point, just fire them up on the Q&A. I'm happy to spend some more time explaining some of the concepts. If I'm using words that are just unknown to you, let me know. I didn't prepare as nicely done Pingo questions as before. It was a little tough for this topic to come up with good ones. But well, it's just a bonus problem, so in case you don't get all the details, you just don't, and no harm's done. So how many different Cartesian trees are there? It turns out, well, because Cartesian trees are binary trees, this number has actually been studied, and it's exactly this number. It's called the Catalan Numbers, after, well, French mathematician, or, well, after a mathematician called Catalan. I'm not sure about his nationality. And he found that you can count binary trees and actually many other objects by these numbers. So, for example, if you have 3 elements, there are 6 permutations. So there are 6 different ways how you can order the numbers 1, 2, and 3. Well, it's 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. But if you work this out, there's only 5 binary trees over 3 nodes. And these are this one, and this one, and this one, and this one, and this one. And it would be a nice exercise to let you map which of these Cartesian trees maps to which permutations. Unfortunately, Pingo doesn't support these types of quizzes. I've seen while playing with Canvas and setting up exams that online quizzes sometimes allow this. But so you might want to do this as an exercise. But we've already seen that this balanced tree down here corresponds to 2 permutations, namely those 2. And that means for the 4 other trees, there's 4 other permutations left. So there's a 1-to-1 mapping between those. But for the balanced one, we have 2 permutations. And this continues. If you go to larger inputs, it becomes much more pronounced that there's some trees that have many permutations for which they are the Cartesian tree. And there's, in general, many fewer binary trees than permutations. Now, this is not a course on combinatorics, even though you might have noticed that I kind of like these games of bijecting between different objects. I don't want to dig into more detail of the Catalan numbers. I do want, however, to discuss a simple upper bound. I want to show you that there's definitely not more than, well, this is a fancy way of saying 4 to the n. I want to convince you that there's not more than 4 to the n different binary trees on n nodes, or the same thing, not more than 4 to the n Cartesian trees on arrays of n numbers. In case you wonder why this makes sense, why this is important for algorithmics, we'll come back to that. All of this will eventually fit together into the big puzzle, and we'll need all those pieces. So bear with me for a second if this is very abstract. What I want to show is we can compute a function that takes a Cartesian tree and encodes it as a special string, namely one that has opening and closing parentheses. And this string will have length 2 to the n if the Cartesian tree has n nodes. So maybe I should be a little more clear about this. So there's an opening parenthesis, that's one symbol. There's a closing parenthesis. And we have 2n of these. Now, this function will be a valid encoding in the sense that no 2 Cartesian trees are mapped to the same string of balanced parentheses, or to the same string. And that means there's not more Cartesian trees than these strings. But these strings, that's really the same as bit strings of length 2n. Which means I can encode a Cartesian tree using 2n bits. And I don't have the same code assigned to any 2 Cartesian trees. That means the total number of Cartesian trees with n nodes is at most as big as the number of such binary strings, and that's just 2 to the length of that bit string. That's how we get to this. Okay, I hope the route is somewhat clear. What remains to be done is to find this function that maps trees to these weird parenthesis strings. And the way how we'll do this is a recursive decomposition. We'll start at the root node. We will take its entire left subtree, And we will apply the function f to this entire subtree. That will give us some result. That will be some string over parentheses. I'm making this up. This is not the right one. Something like this. And then we'll do the same thing for the right subtree. I think I want a different color for that. And we also apply this function to the right subtree. That gives us another string of parentheses. And then we will, for the root node, we will add one pair of parentheses starting before the red part and ending just after the red part. So this blue pair of parentheses separates the left subtree from the right subtree. And this function is defined recursively, so I should say what happens for if I go to an empty subtree, then it just does nothing. Okay, so the function is well defined that way, and I think a little example is helpful for that. So I'll try to squeeze the definition of the function here. And let's start with a smaller example. Let's take this binary tree. We'll start with the root. That will give us some pair of opening and closing parentheses. And inside this, we should put the encoding for the left subtree. That's a single node, so it will be an opening and closing parenthesis pair. And then there's an empty subtree left and right, so this will be just nothing in these two. That will be nothing here and here. So I'm just pointing here because the empty trees, they would go into that spot, but they're empty, so nothing's really encoded for those. Let's go on to the next part. So we have this node. This will again generate an opening parenthesis, but it's inside this subtree, so it can't go before the blue opening one, because it has to stay inside of its own subtree. So we first encode this in isolation, and then we add the blue one once we come back from the recursive call. Again, a single node like the red one, maybe I can give this the same color. That's just another open close. Then we have one more node here. This will also give an open and close. And there's a left subtree that's empty, so that will be nothing in between. And then behind that, we will have another pair open close with nothing in between and nothing behind. So now you might wonder if I can actually reconstruct the tree from this. And this seems easy if I have the colors, but what if I don't have the colors? So let's try to do this, and I'll try to reproduce the same thing. So I hope I copied this correctly. The interesting observation is, even though this is just, it looks like an arbitrary collection of opening and closing parentheses, it has a little bit of a structure. And well, maybe I'll first explain that part. The string we get whenever we map a tree to such a string of parentheses, then this string is balanced. And what I mean by that is it forms a correct expression. You could type this in to, say, a programming language. There's nothing in between, so it might not like that too much. But apart from that, it would be a valid expression. You could take our string that we had. Okay, so this is going to be a longer example, but you could add between two parentheses, you could add arithmetic signs. And then between two, you could add numbers. I'm totally making this up. This doesn't make any sense, the numbers. I'm just saying the parentheses are always so that this is a valid thing. You could type this into a programming language and it would just compute the result. Okay? So that's what balanced means. Balanced means we obtain a valid expression by inserting numbers and pluses. I inserted a number in here. Say I could use 1. And whenever I see this, I add a plus in between. That's my definition of balanced parentheses. Such a string is balanced if I can add ones and pluses and it forms a proper arithmetic expression. It turns out whenever you map a tree to such an expression, it is balanced in this sense. That's just how we construct it. We always add a pair of parentheses that is properly balanced, and then we add 2 more strings which are recursively constructed, so you could prove by induction that this is balanced. Okay, but our actual task here was to show that we can reconstruct the binary tree just looking at the parenthesis string. So try not to look at this guy. Maybe I'll just take it away for the moment. And we pretend it's not there. So I'll move it down here. Oh, I should have moved all parts. Where does that come from? Let's try to do that again. Okay. Now I grabbed everything. So let's put that down here. And let's pretend we don't know the tree and we try to reconstruct it. How do we do that? First of all, we can take every such bounds parenthesis expression and draw it. Whenever we see an opening parenthesis, that means we go a step up. And when we see a closing parenthesis, we go a step down. So, okay, I should have I messed up the spacing a bit, so let me do that again. And then we go down, and we go down. This should come out at the same height. Now we go up a step again, and up a step again, and again. Down a step, and down a step, and then we go 1 up, 1 down, 1 up, 1 down. So, to show this correspondence one more time, this always corresponds to up and down slopes. And then we see, okay, we also have the levels. So there's ground level and then height 1. And this in the example is all that we had, but it could actually go much higher. Yeah. Okay. Now, the rule says we take the first parenthesis is the one here. That's before everything else starts. That's where you still look at here. And now we have to find the matching blue parenthesis, which is the one that brings this walk, which walks up and down, back to the same line. So we're looking at this line, and the first parenthesis that brings us back to this line, that's the closing blue one. And that means we have now found our root node, which corresponds to that parenthesis. And now we have two recursive calls. We have the red part in there, which starts with this node. So it looks at the parenthesis that corresponds to the next up, and then the first one that brings us back down to the same level. In that case, that's just the single thing. So we have a single node here. It's the left node of the blue one because it's inside the blue parenthesis. And there's nothing between those, and there's nothing behind those and before the blue one, so that's a leaf. Similarly, we continue behind the blue one, so we have the next up. This is the next parenthesis. And now we're looking for the first thing that closes that one. Well, we go up, 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 and then this is the one that brings us, this is the one that brings us down to the same level. So that's our green node. And we have two recursive calls again. There's the thing in between, which looks at this. When do we come back to that level? Well, that's a single node, so the left child of this green one is a single node. Then the next step is we look at this upslope. When does it come back to this point? It's just the point after that. So the right subtree of this green part is everything behind this. And the root of that right subtree is this pink guy. Nothing in the left because that's empty. And the right subtree again is of the same type. What brings us back down? It's a single node. So, right subtree. So this should be our tree, and thank God it's actually the same tree. So let's move that guy back up. So I hope I could convince you via this example that we can take any binary tree and map it to such a bit string, well, such a parenthesis string. I can replace open and close by 0 and 1 if I want. So then it's a bit string. And I can also go back. Whenever I have a balanced parenthesis string, I can reconstruct the tree. So one last thing about this is, if my balanced parenthesis string is not balanced, maybe it looks like this. This doesn't correspond to any tree. So there are more balanced parentheses. There are more parenthesis strings than trees because not all parenthesis strings are balanced. There's no way how I can make this into a valid expression. It starts with a closing parenthesis. Come on, what are you closing? That's just illegal. It's not a balanced parenthesis string, so it doesn't correspond to a tree. But that's okay. Our encoding uses more bit strings than binary trees, so it gives us an upper bound of the number of binary trees. Oof, long way to go. I still hope you enjoyed this part a bit. What you should take from this, in case nothing else sticks to your mind, is we can take a binary tree of n nodes. Oh, what's that? No, I closed the Zonal crash. That was the first time this term had to happen eventually, I guess. And now the layout is not the right one. Okay, almost back. Let's see if something in the file was lost. Okay, seems almost everything is here, so that could have been worse. Okay, just save it, please. No, not quite. So I can take any binary tree with n nodes. And I can encode it. I can encode it as a 2n bit string. That's what we will need for the rest of this topic.